All right, so just to recap the problem we worked on in the last video, we were looking at this damp-driven spring. The important part that's new to us is this idea that x should be u1 x1 plus u2 x2, and using our formulas to find u1 and u2. And then the part that I skimmed over was once I found u1 prime, u2 prime, I would have to integrate something very messy, and then I would have to do this algebraic equation that simplifies to something very nice. And I just want to sort of like take us back to thinking about the problem. So we picked to solve this using variation of parameters, and that's fine because it works for second order differential equations. And if we had functions on x prime and x, this would work, but the fact that they're constants doesn't stop variation of parameters from working. But for comparison, last section we learned how to use undetermined coefficients, which would work for this problem as well. And with undetermined coefficients, we would say there's a cosine in our solution, so probably x sub p looks like something times cosine 4t plus something times sine 4t. And then we would say my x1, x2 don't conflict with that. We would set up an algebraic equation to solve, and we would have gotten these same weights right here. So when we do variation of parameters, it introduces a whole bunch of extra stuff that simplifies in the end. If we did undetermined coefficients, we would actually start with this form and then just have to find those two weights right there. And personally, I think the calculus associated with undetermined coefficients would be easier in this case than the one that we have to use variation of parameters for. But that's just down to personal preference. And if, for example, the roots of this equation had been the same as giving us cosine 4t, then undetermined coefficients would probably be harder. So with that little thought that you should always have when you're picking how to decide between the different methods we have, I'd just like to do a quick aside about this method in higher orders. So we technically can use variation of parameters on higher order problems. The only problem is that it becomes very messy. And so the way it works is if y1, y2, down through yn are fundamental solutions to the homogeneous version of this differential equation, the nth derivative of y plus some function of x times the n minus 1th derivative of y, all the way down through some function of x times y prime and some function of x times y equal to f of x. So y1, y2 through yn would just solve when this is 0. Then we still have this special form that the particular solution is u1 times y1 plus u2 times y2 down through un times yn, where uk prime would be equal to wk over w. And then you would just have to compute w, the Wronskian. Oops, there's an A in Wronskian for all these y1 through yn. And wk is the Wronskian, kind of following the same pattern we had for w1 and w2 here. w1 takes out the y1 column and replaces with f. So WK is removing the Y sub K column and using like 0 through F instead. And we'll just look at the third order example to kind of make that a bit more concrete. If you're interested in using this at higher orders, you can follow those rules to make it happen. But I'm just going to give you third order variation of parameters right here. So you would be looking at y2 double, y triple prime plus p2 y double prime plus p1 y prime plus p0 times y equal to f with homogeneous solutions y1, y2, y3. Your Wronskian is going to be y1, y2, y3, and its derivatives to make a square. And then you're going to need to compute W1, W2, and that's going to need more space, and W3. So W1, you're just going to take 0, 0, F, and then everything else the same. W2, you're going to have your middle column is 0, 0, F. Take out all Y2s, but everything else stays the same. And W3, your third column, the one with the Y3s, becomes 0, 0, F, but everything else stays the same. And so you'd have U1 prime is W1 over W. U2 prime is W2 over W. And U3 prime is W3 over W. With particular solution y sub p equal to u1 y1 plus u2 y2 plus u3 y3. And the general solution being c1 y1 plus c2 y2 plus c3 y3 plus all of that. Following the same pattern as usual, it's just a lot longer because we have that third order problem. So I'm going to stop here. Next up is